I'm Dr. Anita, Assistant Professor of Mathematics, Haji Kartaravatar Howdia College, Uttamapalayam. Now we discuss Leibniz theorem in differential calculus. Differential calculus is the branch of mathematics which is from algebra and trigonometry. It built on two major complementary ideas, both of which is critically on the concepts of limits. The differential equation is concerned with the instant rate of change of quantities with respect to the other quantities, more precisely the local behavior of function, which can be illustrated by the slope of functions of a graph. Now we discuss the successive differentiation, otherwise it is called as nth order derivatives. In that example, if y equal to e power ax, if we differentiate y, we get the first derivative, e power ax. In the power, we have a into x. We differentiate x, we get a into e power ax. It is denoted by the first derivative. The first derivative is dy by dx equal to a into e power ax. Again, we differentiate with respect to x. We get the second derivative, that is y2. y2 is equal to d square y by dx square. The answer is a square e power ax. Again, we differentiate with respect to x. We get y3. y3 means d cube y by dx cube a into a e power ax, that is a cube e power ax. Continuing this process, that is continuing, we differentiate up to n times, we get the nth derivative of yn. The nth derivative of yn is equal to y. We write y in suffix, we write n equal to yn. Yn, the answer is a power n e power ax. In the second example, if we have y equal to a power mx, where m is a positive integer. If we differentiate y with respect to x, that is y1, y1 is denoted by dy by dx, otherwise capital D into a power mx. That is the derivative of a power mx. The answer is m into a power mx log x, because we take a log on both sides, we get m into a power x log a. y2 is equal to, y2 means the second derivative of y. The y2 equal to m into log of a, the whole square into a power mx. The third derivative of y equal to m into log a, the whole cube, a power mx. We differentiate n times, we get yn equal to m into log a power n into a power mx. In the third example, if we have y equal to ax plus b power m, where m is positive integer such that here m is greater than n. If we differentiate y with respect to x, we get the first derivative of y1 equal to m into ax plus b the whole power m minus 1. Here we have ax. In that a, here we have ax. If we differentiate ax, we get a. Therefore, the answer is ma into ax plus b the whole power m minus 1. Then we differentiate the second time, we get the second derivative, that is y2. y2 equal to m into m minus 1 into ax plus b the whole power m minus 2. Already in the first derivative we have a. Again we differentiate ax, we get a. Therefore we have a into a, that is a square. In the answer we have m into m minus 1 ax plus b the whole power m minus 2 into a square. If we differentiate that third time, we get the third derivative is equal to m into m minus 1 into m minus 2 ax plus b the whole power m minus 3 into a cube. Again we differentiate fourth time, fifth time, up to n time, we get yn is equal to m into m minus 1, m minus 2, and so on, m minus half n plus 1 into ax plus b, the whole power m minus 1 into an. Now we go to the Leibniz theorem. In the Leibniz theorem, we have two functions. That function is u and v. We differentiate u and v with respect to x up to n times. Here u and v are in product. uv on the nth derivative, the answer is nc naught uvn plus nc1 u1 vn minus 1 plus nc2 un minus 2 v2 and so on plus ncn minus 1 un minus 1 v1 plus ncn un v. We prove this result by the method of induction on n. If we take n is equal to 1, because in the left hand side we put uv first derivative. We use the product rule. Here we use the product rule. That is u d of uv equal to u dv plus v du. In the direct differentiation, we get uv first derivative. We consider here u as a constant and differentiate v, we get v1 plus here we consider v as a constant and differentiate u1. Finally, we have uv first derivative is equal to uv1 plus u1v. If n is equal to 2, that is we differentiate the second term uv2 is equal to u2v plus u1v1 plus u1v1 plus uv2. We get u2v plus we adding here we have u1v1 plus u1v1. That is we have 2 times u1v1. We write this as 2c1 u1v1. The last term which can be written as 2c2 uv2. We assume that the result is true for n is equal to m because by the method of induction we prove n is equal to 1 and n is equal to 2. Assume that the result is true for n is equal to m, and finally we have to find n is equal to m plus 1. Therefore, we assume the result is true for n is equal to m. We have uv mth derivative is equal to mc naught uvm plus mc1 u1 vm minus 1 and so on mcm minus 1 um minus 1 v1 plus mcm um v. Here vm means mth derivative with respect to x, that is dmv by dx, and u1 means the first derivative with respect to x, that is du by dx. u2 means the second derivative with respect to x, that is d square u by dx square. In similar manner, we write u1, vm minus 1, all the things are written like that. Differentiating both sides, we get u, vm plus 1th derivative, mc naught u, vm plus 1 plus mc naught u1, vm plus mc1 u1, vm plus mc1 u2, vm minus 1 plus and so on. The last term is mcm u m plus 1 v. Here we use the result, that is mcr minus 1 plus mcr is equal to m plus 1 cr. And the second result is that 1 plus mc1 plus 1 plus m equal to m plus 1 c1, mcm equal to 1, which can be written as m plus 1 cm. Therefore, in the previous equation, uvm plus 1th derivative is equal to mc naught u vm plus 1. We grouping these two terms, mc naught and mc1. mc naught and mc1, using the result 1, we get mc1 into u1 vm plus again we group mc1 and mc2 and mc m minus 1 plus mc m minus 1. mc1 plus mc2, the answer is mc2, m plus 1 c2. m plus 1 cm minus 1 plus m plus cm, the answer is m plus 1 cm. Using this, we substitute these answer in the equation, we get m plus 1 C naught U Vm plus 1 plus m plus 1 C1 U1 Vm plus and so on m plus 1 Cm Um V1 plus m plus 1 Cm plus 1 Um plus 1 V. Therefore, the theorem is true for m plus 1. Hence, we prove the result is by proved mathematical induction. The theorem is true for any positive integer n. Using the result, we see the one example. If y is equal to sine of m sine inverse x, then we prove that this one. We put y is equal to sine cos of, that is the first derivative is equal to cos of m sine inverse x m into 1 by square root of 1 minus x square, because the derivative of sine inverse x is equal to 1 by square root of 1 minus x square. Therefore, the square root of 1 minus x square multiplied by y1, we get square root of 1 minus x square y1 m cos m sine inverse x. And we take the square root or square on both sides. We get 1 minus x square y2 is equal to m square into 1 minus y square. Differentiating both sides, we get the result. And applying the Leibniz rule, that is yn plus 1, yn plus 2, yn plus 1, and so on yn, we finally get that result. Thank you.